All right, welcome back, everybody, to our bi-weekly program of Hack Central, included in our Tech Bytes program. Glad to see you guys coming back. If you are new, welcome to Hack Central. Hack Central is essentially a computer science program we run on top of our Intro to Programming and web development courses as well. And through Hack Central, we like to deep dive into some more advanced computer science topics, which we aren't able to cover in our other courses. So specifically, you'll find us doing some cooler things, in my opinion, such as going into machine learning. Last 2 weeks ago, we did some stuff with automation and seeing how the computer can draw an image without me even pressing my keyboard or the mouse. Some pretty cool stuff. If any of this stuff excites you, I'm glad you're here. Or you can find some of our previous videos as well on the Schomburg Library's YouTube channel. But other than that, glad you guys are here. And without any further ado, let's get to this week's Hack Central. All right. So to introduce the theme of what we shall be covering today, that is going to be a different machine learning algorithm, which has a bunch more differences than the ones we learned about in the past. So in the past, we've learned about linear regression. We learned about k nearest neighbor. We've learned about the k-means algorithm. We learned about the differences between supervised, unsupervised machine learning. And today, we're going to be taking a dive back into the machine learning algorithm phase, learning about an SVM algorithm. Now, what does the SVM acronym stand for? Well, it stands for Support Vector Machines. And this algorithm has a bit of nuances. And if you've been here from the start learning about our other algorithms, you'll find that to understand this algorithm, it's going to be much more easier. And the concepts, the key ideas will be similar with some new and cool things. So let's get to it. All right, if you guys don't already know who I am, guys, my name is Rayaan Siddiqi. I am a senior at James B. Cohen High School. I love to program, made multiple apps for the App Store, made a dozen different websites, and really am looking towards the content creation side, making videos for my own tech YouTube channel, running a sports talk show with my friends, and writing articles on the internet as well. If any of this sounds interesting to you, you're more than welcome to check out my website at rayaansiddiqi.com. And if you are wondering what are the other programs I was referencing earlier on today with Tech Bytes, you can find them right here. Our first main program is the Tech Bytes Intro to Programming and the Web Development course. In our Intro to Programming course, guys, we go over the language of Python for almost now 4.5 months. We've been learning about the fundamentals, making awesome projects, just like we are right now in that class. And that program goes on every other Monday. It's a bi-weekly program from 3:30 to 4:30 p.m. And our web development course is an every Wednesday type of course. So you'll see me there every single Wednesday, 3:30 to 4:30. The times are shifted a bit back. If you remember, they are a bit different in this month of October because we're just trying to accommodate, with school starting, giving everybody a quick breather after school ends. And then we also got our teen trivia program, which is a nice way to kick off the weekend and relax. We have this program every other Friday, meaning this is also a bi-weekly program where we play a game of online trivia, which is usually some type of theme. And then it's your chance to place in an online leaderboard and see who knows and who has the most general knowledge. So if any of these programs excites you guys, I highly recommend you go to the Schomburg Library's website in the events page and sign up. All right, so now let's get towards our topic for today, that being about the support vector machine algorithm. So how about we first get started by how are we going to be utilizing this algorithm and how will we actually be coding it? Well, if you guess the language of Python, you are 100% correct. Just like our linear regression algorithm, the k-means, the k-n, we use Python and this algorithm is no different. If you're wondering why are we utilizing the language of Python once again, well, it's mainly because Python is super nice when we are implementing machine learning algorithms. It is very easy to use other frameworks, libraries in conjunction to make an algorithm work correctly. And also, Python has a bunch of awesome libraries which we can use when visualizing our data, manipulating our data, and making predictions and classifications, such as NumPy, Keras, TensorFlow, Matplotlib, all these fancy names for libraries which have a very critical role in writing these algorithms and putting them into actual applications. So we have laid out that we're going to be using the language of Python, but how about we actually talk about what is the support vector machine algorithm and what makes it truly different than the ones we've learned about in the past? Well, funny you ask, because that's what we're going to cover. So, the SVM algorithm is another clustering algorithm through which we can make classifications given data sets. So, if you remember, like the k-means algorithm, the KNN algorithm, both of those were used to make classifications on data sets, such as classifying is a car in a good condition? Is this house worth this much amount of money? Unlike the linear regression, remember that algorithm is towards making predictions using a line of best fit. This SVM algorithm fits the general bubble of the k-means and KNN algorithm because we are making classifications. Now, the key difference which comes into play is that unlike the previous algorithms we have learned about, like KNN, K nearest neighbor, and K means, those algorithms have data limits. This is something we've talked about. We'd always like to talk about the limitations of what we are learning. And the limitations with those two algorithms is that they are very size limited, meaning they cannot perform very big computational problems. So say I have a data set with hundreds of thousands of pieces of data, which is really realistic. If you think about it in a real world application, guys, we have our phone right here. We got devices at the tip of our fingertips. We use apps on an everyday basis, whether it be a social media app like Facebook, YouTube, Snapchat, Instagram, or whether it's just a game which has an online leaderboard. If it's a big game or it's one of these apps, there are hundreds of millions of users. And in order to make predictions based off the users and give you curated content and recommended items on your recommended page, like a recommended video on your YouTube page, that has to occur through machine learning and making predictions, classifications. Well, the KNN and K-means algorithm are not the best fit if we put it into that context because we got a lot of data, to say the least, right? However, the support vector machine algorithm, aka the SVM, is a much better fit in that case. SVM actually works amazingly well with large pieces of data, meaning data which have hundreds of millions, hundreds of thousands of pieces of data. SVM is awesome in being able to predict and being able to classify where certain data pieces belong. And I got a little note to the right here which says this algorithm works very well with high dimensions of data. Now, what does that mean? Let's dissect that statement. So I'm saying that the SVM algorithm is able to work very well with with data which is in high dimension. Well, what does that actually mean? Well, I want you to think about dimensions are essentially 1D, 2D, 3D, 4D. Sort of like if you ever visit a movie theater, right? You can watch the movie in 2D, or you could watch it in 3D. You know, they give you the glasses and you can watch it in 3D. It makes the movie content seem like it's popping out at you. Or if you ever watched a movie in 4D, in a sense, you know, that's like the whole other level. Your seat is buzzing, you got the audio, maybe your headphones plugged in, your seat's going up and down. It's a whole other experience. And similarly, as we keep on going up the experience in dimensions of data, SVM is like, okay, I can do it. I can do it. The support vector machine algorithm is perfect in conquering large pieces of data. So now let's talk about how does this SVM algorithm actually work? We've learned about in the past how linear regression, it uses a line of best fit. K-means and K-nearest neighbor, they have a similar type of process using the distance formula, seeing how far points are from one another and checking and comparing the least distance to classify data points. However, the SVM is a bit unique, and personally, I would say understanding an SVM is sort of the easiest. Although the math, which we're going to get into later in a bit, is a bit more complex, the basic idea behind a support vector machine is much simpler. Now, why is that the case? Well, to talk about how this SVM works, we have to first get to know this idea of hyperplane division. Whoa, hyperplane division. That sounds like a word that's made up, right? Well, it's sort of not. Let's break it down. So, the way our support vector machine algorithm works is that it divides data into specific classes, meaning dividing, say we have a car, trying to classify whether it's a amazing condition, best condition, moderate, least, or super least, right? Trying to classify that into certain areas. Well, in order to do that, we use a thing called a hyperplane. Now, hyperplane is a very fancy word for a line which simply divides data up. So say if I take the annotation tool out, We have some data right here, right here, right here, right? And the hyperplane is essentially going to just create a line as sort of think about it like a partition in real life. It's like a block or something which is going to divide our data physically up. And similarly, a hyperplane does just that. And basically, guys, in 2D, meaning two-dimensional space, a hyperplane is just a line. In 3D, a hyperplane is referred to as a plane which is dividing up our data into separate classes. And then if we have the really cool dimensions of data, like 4D or even 5D going up on our degrees of data, then we refer to the thing dividing our data up as a hyperplane. So don't get too confused or too caught up in this idea, wait, this hyperplane concept sounds new, or what does it even mean? Just remember the basic core idea is that the SVM algorithm is able to function through a partition or a divider separating our data up very nicely. And this is a bit different than our other algorithms, which we have learned about. And speaking of those other algorithms, how about we talk about the similarities and the differences between the other classification algorithms like the KNN and the K-means? How about we start off with the similarities? For one thing, all three of these algorithms are trying to cluster and classify data. At the end of the day, regardless of how they get the job done or with however much data they can get the job done, the goal is the same. They're going to classify data into separate pieces into separate classes. However, the differences are where there are some more differences, obviously, compared to the similarities, and that is because the KNN and the K-means algorithm, they are both supervised and unsupervised machine algorithms, unlike an SVM, which I believe is an unsupervised machine learning algorithm. But the main difference is that the KNN and K-means, like I mentioned before, they do not work well with large dimensions of data. The example we provided earlier, talking about if we are managing and predicting and making classifications on very large pieces of data sets involving hundreds of thousands of pieces, KNN and K-means are not the best option because they cannot handle and make accurate classifications with a high accuracy score with that large amount of data. However, our algorithm, the SVM, is great, like we mentioned before as well, works great with high dimensions of data. Just remembering, and this slide just wants to iterate that point that although we are learning about many algorithms, which although may have a sort of similar goal, like we talked about that the KNN, K-means, and SVM, all the goal is the same. They want to classify and cluster data. They always usually have a little bit of nuance separating them. And today, that nuance is a major one, that being that the SVM works great with large amounts of data. All right. So now let's talk about how does this SVM work? And if you've been here in the past with Hack Central, I usually like to draw it out, give us a visual representation, get to know how our data set is able to be classified or some predictions are able to be made. And we're going to be doing exactly that. So let's get off by starting. We talked about the idea of how a hyperplane divides our data into separate classes so that we can identify whether, like going back to the car example, whether a car is a good price car, a good value car, considering multiple inputs, or maybe it's not a good valued car. Well, the way that partition or that divider is able to be created is that first we need 2 points. Specifically, we need 2 points which are an equal distance away from the dividing that partitioning line. Now, these 2 points, which I got circled, if we take a look at the image towards the left, this blue and this orange point, these 2 points are going to be the points we select because they are an equal distance away from our dividing line. If I turn the pointer, we can see that's a couple centimeters right there, a couple of centimeters right there. And once these 2 points have been selected, we give them a very special and unique name. We refer to them as our support vector points. So remember that these 2 points, which are an equal distance away from our partitioning line, they are referred to as support vector points. And now you might be noticing, wait, why do we got a second image towards the right? Like, this image looks perfectly fine. This hyperplane, we got 2 points which are an equal distance away from our dividing line. Well, you're right. we can use multiple hyperplanes, and we'll talk about later how we choose which hyperplane to go with. However, we can definitely create multiple hyperplanes which divide our classes up. However, the main thing when it gets down to choosing one over the other is going to be a thing called margin, which we're going to discuss in a little bit. However, if you are thinking that both of these images are correct, you are 100% right, because we indeed can create multiple hyperplanes which fit the parameters of our data set. And in this case, we got a diagonal hyperplane. In this case, we got a vertically straight hyperplane, both of which are valid hyperplanes. So here comes the idea now. How do we specifically choose which hyperplane we're going to go with? Like, both of these are, although they're valid, they're dividing our data up correctly, right? Because we can obviously see all of the purple colored points are on one side and all the orange colored points are on the other side. So that means our hyperplane is doing a fine job, but how do I know which one to go with? Well, out of these two hyperplanes, we would go with the first image, that aka being the one towards the left. Well, why are we going with the one towards the left? Why am I specifically choosing this left hyperplane? Anybody have any ideas? Why do we think that this hyperplane is better compared to the one towards the right? Why is this one greater or better than the one towards the right? You can drop your thoughts. No answer is a bad answer, guys. We're all going through this together in the chat or in the Q&A as anonymously, whatever you prefer. Feel free if you have any idea, just drop it. You can even anonymously message me. All right, yes, and the reason why the left one is the right one, the one which we are favoring and going to choose, is because, like you guys mentioned, is that the distance between the two support vectors, aka these two support vector points, and our hyperplane is the largest. So whenever, guys, that distance between our two vector points and our hyperplane is the largest, that is when we know which of the two hyperplanes we have to choose. And although in this case it may look like that the distance between our support vector points and our hyperplane is about the same, there is a slight difference I try to distinguish when drawing these images, is that the left one does have a greater distance between the point and the line, which is why we are going to be selecting this first image as the one which is going to represent which hyperplane we are going to continue with. All right. So now let's get down to what is the difference in the distance called. Like we just talked about in the previous slide, that we are selecting a hyperplane based on whichever has the distance greatest between the support vector point and the hyperplane. And that distance, that difference between the distance between the support vector point and the hyperplane is referred to as the margin. Now, basically, guys, the margin is the distance which is going to separate all of the majority of our data points in our data set compared to our hyperplane. And the main key being that the greater the margin, the better and more accurate classification is going to occur when we run our Python script. So if we take a look right here, the margin is pretty nice right here. This blue line is separating the majority of our data points and the hyperplane. And since this looks like a good margin of space, the more space we have, which separates our data points and our hyperplane, that is going to yield a higher percentage of accuracy. And at the end of the day, guys, remember, the higher the accuracy, the more accurate classification which we can get to occur through tweaking our parameters and data is always preferred, because we want to make sure that we are, so if we put this into a real world example, right, we want to recommend a good video and classify the user into a correct group of people rather than in an incorrect group of people, right? So in order to do that, we want to make sure that we have the greatest margin And whenever we have a larger margin, we know that our classification is going to be occurring more accurately. All right, so now let's discuss some of the important mathematical concepts regarding our SVM algorithm. Now, usually you might be noticing that, hey, we don't really go into much math with our Intro to Programming course. Fun fact, in our web development course, we did go over some cool math about 2 weeks ago when we were working on our calculator project regarding some trigonometry functions. However, if you're from there, you're gonna have a leg up here because you're gonna understand some of these concepts. Now, I'm not going to be going on to the whiteboard and drawing these concepts out because they are a bit much more complex than what we have previously done, simply because they are some high school level math concepts, which I do not want to bore anybody, trying to keep everybody's interest here. But basically, there are three basic foundation mathematical concepts which we got to understand. The first one being that we have to calculate our length of our vectors. Sort of in the name, right? We got support vector machine algorithm and we got support vector points. Well, in order to calculate the distance between the points and the data points, we like to use basically, if you have heard of the Pythagorean theorem in a sense, say we have a vector which is going to be represented as x. And in order to calculate the length of that vector, what we're going to do is we'll do the length of the x component squared plus the length of the y component squared. And x is going to be the length of our vector. And remember, this is going to help us in determining the margin, seeing which hyperplane, all that we're going to be choosing. Secondly, we want to see which direction our vector is pointing towards. So if you think about, get the highlighter tool, the annotating tool back out, we usually have 4 quadrants, right, in a 2-dimensional type of mathematical setting. Well, in order to determine which direction our hyperplane is it going like this? It's going like this, like that. In order to determine that, which quadrant and which quadrants through the hyperplane will be going, we like to get the direction of a vector. And a vector, the cool thing about a vector is that not only is it a number, but a vector also has a sign. So it has a positive or negative sign, which tells us the direction of our vector. And lastly, we use an important concept called dot product, which is a bit complex. Uses some trig functions, the length of our vectors, using all these concepts together. But basically, dot product is going to tell us how our two support vectors are related. Now, this is very critical because of number 1 and 2, length of a vector and direction of a vector, they both allow us to get to the third concept of a dot product and realizing how are our two support vectors related in order to see where is the hyperplane going to be created, where is the margin the greatest, so that we have better classification occur. And dot product returns to us a numerical value. It's like a scalar value in a sense, and using that value, our computer is able to essentially put our hyperplane wherever it correctly belongs to yield us the highest percentage of accuracy. Which, remember, this concept of accuracy is important because we want to make sure that we have the highest accuracy when classifying data. Because if we don't, why are we even trying to classify, right? We want to classify to make an impact, something which helps other applications. And that's the main key with all these algorithms as we go through these. All right, so how about we run an example? Always like to run a Python script going through our algorithm. And today we're going to be going over the SVM algorithm. And specifically, our scenario is going to be, we're going to be classifying the severity of a patient's condition, such as this is relating to if they are susceptible for a disease like cancer, or if they are not, which type of percentage are they located in? So without any further ado, I'm going to load up my Python script. There we go. All right, so here is the Python script. You may notice that there are a bit of similarities from before. We are using a library called the sklearn library. Remember, sklearn is an awesome Python module which helps us importing data sets. Data sets are basically, we don't have to go to the internet and scour the internet for data sets. sklearn is a library which has thousands of different data sets, which we can simply just preload like such right here. And specifically, remember I was talking about, we're going to be seeing how and where does a person fall classification-wise if they are susceptible for a disease like cancer. And here is where the main difference comes. We've talked about some other algorithms like the linear regression, k-means, knn, and basically they all have a classifier which we use, right? And today that classifier is the SVM, aka the Support Vector Machine Classifier. Some simple stuff right here, guys. We are dividing our data up into training and testing data, making sure that the training and testing data is separate. Never want to get those two cross-contaminated in a sense. Don't want to make sure that testing data appears in a training and vice versa. And then we're going to be making some predictions based off of our testing data and measuring the accuracy of our data. And if I hit run right now, we see that the accuracy of our data right now is in 92%. Now that's pretty good. Anything, I mean, 92% on a test is pretty good, right? Well, 92% similarly right here is really good as well. However, there's always the chance of getting a better and more accurate score. But how is that possible? Like, we just wrote the code, we can't manipulate anything, right? Well, there is something which we can do. That being, if our data is not perfect, meaning if our data is not aligned in such a manner where we can specifically divide our data nicely using a hyperplane. So in this case, we take a look, we got 3 different pieces of data. They're all mixed and clustered all over the place. This is not a perfect and ideal data set. However, there is a pretty cool technique we can use to make sure that we can make it into a good data set. And the way we do that is using a technique called kernels. Not popcorn kernels, if you have that in reference, but kernels. Well, what does kernels do? Well, kernels allows us to bring our data up another dimension. So essentially, if we have this data right here, it's in a 2-dimensional data set, we can knock it up another degree, bringing it up to a 3-dimensional data set. And once we use kernels to up the dimension, the degree of our data, we hope that our hyperplane can correctly fit our data into specific classes. So using this idea, if I open up my Python script once again, and I head on over to a separate script I have with just a little bit of syntax difference, that being I am declaring and passing a parameter of using a linear kernel. Do not mind the linear word. It's not really important right now. We don't have to talk about that. But essentially, I'm going to use a kernel. And my hope is that with using the technique of a kernel, we get a higher percentage accuracy. So if I use the same code, just applying a kernel, run our data set, we get an accuracy of 92.1. So I believe a bit similar to our other without kernel, but looks like in this case, our data set was not probably really that large. If I run this again, let's see what happens. So we get a higher percentage accuracy score, nearly 94% as compared to that 91%. And the main thing is that using kernels looks like that our data set was better able to be fitted once we knocked it up a degree. So potentially once we knocked it up to 2-dimensional data, to 3-dimensional data, looks like that our data set was able to be more accurately classified. And this case looks like it was accurately classified 94%, which is pretty good. All right, guys. So that does conclude this week's Hack Central program where we discussed all the ins and outs about the support vector machine, aka the SVM algorithm, going through what it's all about, the hyperplanes, the margins, talking about how a hyperplane is made, writing our own script, and then talking about what if our data is not perfect and the cool techniques which we can use to make sure that our data does indeed is able to be classified. As always, hope you guys had a great time. Enjoyed this week's cool algorithm we talked and went more deeper into. As always, guys, I would love to see you guys in our intro to programming and web development course. Would highly recommend you guys sign up for that if you had any interest in this program today. But as always, guys, take care, stay healthy, stay safe. I'll catch you guys on the next one. See you guys.